Okay, so imagine that space is like a movie, and these are different regions of space. And here's a light particle that's traveling in a straight line through space. So the particle is traveling in a constant space, but we know that we may not know the position of the particle, of the photon, but we can know that its trajectory is going to maintain basically a straight line unless some force acts upon it to change its trajectory. Or space curves. So the idea is that a particle has a random walk. It has an equal chance, of moving in any given direction, deviating in any given direction. But its random walk is nullified because the chances that it goes in each of these four directions is 25%, and over time that nullifies its trajectory and it maintains a straight line. In the case of gravitational lensing, we have a mass represented by the red, and so a particle moving through space is curved by the gravitational field towards the mass, and that's called gravitational lensing. So that's a photon being curved by a mass. Now, my argument is that space is basically quantized, and this is not even something I need to prove, because we know that acceleration and gravity will both change the clock rate of a clock. So if you put a clock on a satellite, we know that it's going to move more slowly because we know the clock rate is going to move faster because it's on a satellite in space, because the gravitational field is less, and we know that it's going to move slower because the satellite is actually accelerating through space around the Earth. So when we calculate the clock rate of a clock on a satellite, we have to both calculate how much the decrease in gravity is causing the clock rate to speed up, and how much the increase in acceleration around the planet is causing the clock rate to slow down, and so that we can calculate the difference. But the idea is that space is quantized into different time. It's not the same time in every area of space. So if you have a movie, that would mean like in each frame of the movie, maybe the movie is 24 frames per second or 40 frames per second or 30 frames per second. In each frame of the movie, the whole movie changes. All the pixels in the movie change at the same frame rate. But in space, because we have time dilation, is like we have more frames in one frame of the movie, in one pixel of the movie, and for each interval that frames are changing in another. So if we have one frame changing in this part of the movie, we have 8 frames changing over here, which means this part of space is accelerating faster, or it's accelerating faster, or it's moving faster through time because it's experiencing the strength of the gravitational field. And so that's time dilation on a macro scale. And quantum gradient time crystal dilation is saying that time dilation on the quantum scale basically means that the effect of gravity is increasing the number of time frames, or the delta of time, in some region of space. And so the random walk, while the particle maintains a straight path through a gravitational field that's approximately equivalent in all directions, when you have a mass that's increasing the delta of time to like 8, it's like saying, okay, well, the particle is randomly going to move in each direction, but it treats the direction of where mass is like it has additional directions. That's like, so the particle could move in this direction one time, this direction one time, this direction one time, and in this direction 8 times. And so it's no longer like the particle is moving in each direction 25% of the time, and those 4 directions are canceling out. Now the particle is moving in this direction. Let's see. So we count 10, 11. 1/11th of the time the particle is moving in this direction. 1/11th of the time the particle is moving in this direction. 8/11ths of the time the particle is moving in this direction. And so the median, the average, is that the particle is more often going to be moving in this direction, and thus the path of light bends towards mass. And so my argument for quantum gradient time crystallization is that quantized space that's moving in different rates of time at the quantum scale is changing the trajectory of light, because the random walk is going to result in the light's trajectory being bent towards the mass. And so we argue that it's argued that mass is curving space, but what I'm arguing is that mass is curving time. So the particle's trajectory is being curved by time, and that theory is called quantum gradient time crystal dilation. And I just wanted to explain it as simply as possible so that even a 6-year-old could understand it. Thanks very much.